In this video, I'm going to work through a few of the practice questions that I handed out last week to help get your mind focused on exam questions. We'll do a quick review early next week and then have our exam on next Friday. So first off, we're just starting with some antiderivatives. I know it says to find the general solution of each differential equation, but hopefully you recall the general solution of a differential equation is simply an antiderivative. And make sure that you include your plus c when you're done. So in problems like 1 and 2, those are pretty straightforward. If dy dx is equal to 2 over x to the fourth, I might think of this as 2x to the negative fourth power. So that means that y by itself would have to be 2 times x to the negative third divided by negative 3 plus c. And we can simplify from there. Maybe call this negative 2 over 3x to the third power plus c. And there's our general solution to the differential equation. We know that this is a solution because the derivative of y, or dy, with respect to x of this equation ends up giving us this expression here. And because the plus c, the c quantity is unknown, there's a whole family of functions here that we don't know the precise solution to, and that's why we'll stick with calling it the general solution. So as a reminder, we jumped from this step to this step by applying an integral. So we're effectively, we could effectively use this symbol to indicate that we're finding an antiderivative or an integral on both sides. That's how we're ending up with y, and the antiderivative of the opposite of cosine is the opposite of sine plus c. So not a whole lot of work needs to be shown for those questions. We're literally just kind of working through and finding those antiderivatives that are pretty straightforward. Starting with question 5, you have to be careful though, because if you didn't notice it right away, I'll point it out to you that this is a secant function being evaluated at y, not x. So not our independent variable, but our dependent variable. So up above, we were trying to find the function y with respect to x. Well, here, the derivative of y with respect to x is actually based on the function y itself. And this is what we were calling a separable differential equation. I'm giving you the heads up that this is separable. So with separable differential equations, that's where we usually grouped all of our y components on one side of the equation and any of our x components on the other, x components and constants for that matter. So if we multiply both sides by secant squared of y and both sides by dx, the differential of x, then we now have secant squared y with respect to y is equal to 1 with respect to x. And here again, if we apply an integral or an antiderivative at this point, we can start to get y by itself. You'll recall that secant squared looks familiar. The antiderivative of secant squared is tangent, but here again, it's tangent of y. And the antiderivative of 1 is x, since we're deriving, we're integrating with respect to x. So now we have tangent of y equals some x plus c. So to isolate y, we can apply a tangent inverse on both sides of the equation. And I think this is a fine solution to the differential. Now this is good because we have isolated y. In the event that it can't be done, or if the instructions allow you to leave it in implicit form, then this would be just fine. You know, technically when we apply a tangent inverse, we have to worry about domain restrictions and that sort of thing. So if the test questions, or if I decide to get picky enough to worry about that for next week, I may tell you just to leave your answer in implicit form, and this is what I mean. We're allowed to have a y value not completely isolated, but in terms of some simple function or some basic function. Now moving on to number 7, here again we would have to separate, if possible, the variables here. So I think I can divide the y to the left side and I can multiply the dx to the right. That'll leave me with 1 over y dy on the left side and 2x dx on the right. And if we apply an integral to both sides of the equation here, now the antiderivative of 1 over y is the natural log of y. I will include my absolute value bars here because I don't know if y is positive or not. It needs to be when we use that, that logarithm. Then the antiderivative of 2x is going to be 2 times x squared over 2 plus c. Of course, that's going to simplify, so we now have natural log of y equals x squared plus c. The trick or the technique that we use to simplify from here, we saw this a bunch in class, is to use a base of e as an exponential to eliminate the e in the natural log. This is kind of like the loop rule that we had talked about last year in our trig class, but really we're applying exponentials as a base, acting as the inverse of the logarithm to isolate y. And we now have e to the x squared plus c. Now this is okay, but we did mention in class that e to some power, or any base raised to a power, where the power illustrates the sum of two quantities, that would be the same as the product of the bases. So e acts as a base here. Those are multiplied together, and then we can have two separate exponents. Then here again, e to the c power, well, that's e raised to some constant, which would compute to another constant in and of itself. So we might think of this as e to the x squared times some other constant, and I've been using a star on occasion. If this c quantity keeps changing throughout a problem, I just relabel it as c star. Because it doesn't matter, and we don't really know what the exact c value is at this point. It doesn't really matter what it is. C just stands for some unknown constant, some single numerical value. So if you want to use the star, that's fine. If you want to drop it, that's okay too, especially since we've seen a bunch of these already. So I think reporting this would be just a fine answer. Now I will note that if you're worried about the disappearance of these absolute value bars, we can account for that by considering both a positive and negative e to the new exponent over here. And then interestingly, that plus minus sign, whether we have a plus or minus sign in front of our answers, that can be absorbed by this new c power or c coefficient. So it may be positive, it may be negative, based on our initial quantities if we were ever supplied that. So I just dropped it out of habit and simplicity's sake. I'm okay with you doing that at this point in the class too. Just keep in the back of your mind that there may or may not be some domain restrictions for us to worry about. On the next page, we start talking about slope fields, and we have two of them. I'll work through number 9. It says, for each problem, find a differential equation that could be represented with the slope field. Now, this one's a multiple choice question, so that's going to be helpful. And I think it's a good idea just to kind of work through these and see if any of these differentials can be represented by the slope field. So I'll note that each of these slope field indicators occur at multiples of 1, so that makes things a little bit easier. If I just start picking some arbitrary quantities to substitute into the equation, we can start checking the slope field. So when x is 0, for example, 1 divided by 0 is undefined. So anywhere along this position here, I should see slope field indicators that indicate an undefined slope. Well, an undefined slope would be a vertical slope. So a vertical tangent line. And in this case, we have a couple of them where the slopes are defined. So I know right off the bat that in this case, this is not a good choice for our multiple choice option. When I switch over to B, x squared, so at any x position I would square it, and that's the only indicator of slope. So 0 squared should have a slope of 0 here. 1 squared should have a slope of 1, and 2 squared should have a slope of 4, or something close to vertical. I didn't see any slopes indicated here, so I think they're laying flat in each of these cases, kind of at or underneath this axis line. We can't quite see them. If I were to jump up, then we start to see another disagreement. Immediately here, the x value is 0, so I should see a slope field indicating 0. Here the slope is positive 1, positive 4 again. So these slopes don't appear to be lining up, so I don't think B is a good choice either. Moving on, if C is a good choice, then all we need to do is figure out our slope field quantities based on y. In this case, y is 0. So when y is 0, we should have an undefined slope. That one should be vertical, but this should be vertical and vertical and vertical as well. So I'm not quite sure about that. If we move on, when y is positive 1, well, negative 1 divided by positive 1 should have a slope of negative 1 in each case. Well, those look fine. And if y was negative 2, or was 2, then each of our slopes should be negative 1/2. Well, those are looking pretty good. Now, if I switch down to a y value of negative 1, each of these would simplify to 1 over 1, which is positive. And then these simplify to 1 over 2. And those all look pretty good. So I'm starting to like C, although this one was a bit confusing for me here, because just a minute ago I got to thinking that we can't quite see them, but maybe there are some horizontal slope fields in this position. But now I'm starting to think that maybe there aren't any slope fields at all. Maybe they're not being shown because the result is undefined. Well, before I commit to that as an answer, let's go ahead and check part D. In this case, the slopes are dependent upon y values alone. So again, here we have a y value of 0, so all of our slopes are undefined, or a vertical slope at that position. At a y value of 1, then we should have a slope of 1. Those already disagree. And then at a y value of 2, we should have a slope of 2 at each of these positions. And those continue to disagree. Negative 1, negative 2, and so on. So I don't think any of those are very good at all. So I'm throwing D out as well. So I definitely don't agree with A, B, or D. C was a little bit confusing because of this horizontal line here. Personally, I would have preferred to see the software generate these vertical asymptotes here, although that one's undefined, so we'll leave that one as a dot. But these, well, I guess there's nothing wrong with calling that vertical as well. Yeah, I think that's fine. I would prefer to see a vertical slope field indicated there, and that way it'd be really clear for us to determine that C is the correct answer. Now for the remainder of this worksheet, we just have a bunch of practice problems or applications. Oh, and by the way, there are some solutions for us down here that we could check our work against. I forgot that I did include that in our printout this week. But let's take a look at these differentials here. Atmospheric pressure decreases approximately exponentially as elevation increases. So if we're careful, we can actually start defining our variables at this point. Pressure, I'm going to call that my dependent variable y, and elevation, I'm going to call my independent variable x. So pressure decreases exponentially as elevation increases. So that description actually tells us a lot with regards to differential equations. We know that the equation y, if pressure varies exponentially as elevation does, then our equation y is going to be some sort of exponential format here. But that also tells me a little bit more too. If a function grows exponentially, then that function's derivative grows linearly. So there's a linear change in the derivative itself. And I already made a little bit of a mistake. I got my variables in the wrong spot here. So this should be k times y. So a percentage or a portion of the pressure is how much we would increase or decrease by as our elevation changes. So this is a differential equation. If I left this as kx, then the antiderivative of this turns into a power example, and we're not saying that it grows at a particular power like a quadratic or a cubic. No, we're saying that this is supposed to grow as an exponential. So that's an indicator that a constant multiplier by the existing pressure indicates the pressure change as elevation changes. So go with me here on this. You'll see what I mean in just a second. Now, if the derivative of y with respect to x is equal to k times y, this too becomes a separable differential equation. We can bring the y's to the left and the x's to the right, leaving our constants on the right side as well. So we've got 1 over y dy is equal to k times dx. And if we integrate both sides, we now have the logarithm of y equal to kx plus c. And just like we saw in an example before, we can use a base of e on both sides of the equation. This is going to turn into y equals c times e to the kx power. And here's our exponential growth, where x is going to be acting as our elevation, and k is the rate of change, and c is our initial quantity, or our initial pressure. So as I keep reading, I'm going to ignore this 12% for a second because I'm looking for a quantity that can help me identify C, our initial condition. The pressure at sea level, I'm going to assume that that's an X value of 0 or an elevation of 0, is 761. So what we know is that 761 is the result of some C value times E to the rate of growth times the elevation of 0. Well, this elevation of 0 times k is also 0. E to the 0th power goes to 1. So that effectively factors out and disappears. So we now know that C is equal to 761. So that tells me our formula is a bit more refined at this point. Y must be equal to, in this scenario, 761 times e to the kx power. Now we just need to find k, our growth rate, or in this case, our rate of decay. Now they came straight out and told us what that would be. So our k value is 12%. So we've got y equals 761. That's our pressure at sea level times e to the k power. Now k is going to represent our growth rate. In this case, we're growing at a rate of negative 12% per elevation change. And I think it's x elevation in kilometers. And so now we've got ourselves a more or less complete function. For the final part of the question, we're being asked to evaluate or determine the pressure at 2.7 kilometers above sea level. So we're effectively evaluating y at 2.7. So 761 times e to the negative 0.12 times 2.7. That expression should get us there. And my calculator off screen is showing me 550.3994. And this is measuring in millimeters of mercury. So it took us a while to get there. We needed to use a description of the problem to establish the relationship of slopes or derivatives. Then with that differential equation, we can find the general solution. With some given information, we could then nail down our exact solution, or the solution based on the initial conditions. And then with that new equation, finally, at the end, we can evaluate it to answer a new problem. So let's try number 13. So in this case, we have an isotope of curium that decays at a rate, okay, so that's a good clue, proportional to the amount that's present. So if I let y represent the amount that's present, so y is going to be the mass in milligrams, so y I'm going to say is mass in milligrams, then we'll let time be represented. We can use t for time or x for time, whatever you feel like. We'll say time in thousands of years. That way we don't have to write any real large numbers here. But the rate of change, so the dy with respect to t, is proportional. Proportional is that clue that I know that there's some constant value that multiplies by the amount of material that's present. Well, we just said the amount of material present is equal to y. And so now we have ourselves a differential equation that looks like this, which is remarkably similar to what we saw a few moments ago. So we can go through the same process. 1 over y dy will be equal to k dt. And when we integrate both sides of the equation, we're going to be left with a natural log of y is equal to kt plus some constant. Raise both of these sides to a power over a base of e to cancel out our x or our logarithms here. So that leaves us with y equals c times e to the kt. Here again, this c value is not the same as this c value, but it is a c value nonetheless. It's some unknown constant, some numerical quantity. So there's our general solution, and we're told that the mass was 317.2 3.3 thousand years ago. The current mass, oh that's helpful, is 195.6. So I'm going to use that one. 195.6 is equal to c e to the k times 0. So not 0 years before, or 0, or not some number of years before or after, but 0 being our current time. We saw this before. This term goes to 1, so it must be that c is equal to 195.6. So now our solution, our general solution, is a bit more refined, 195.6 times e to the kt power. We back up a little bit, we see a clue here that 3.3 thousand years ago, the mass was 317. So apparently we were at 317.2 when we had currently are at 195.6. We don't know the rate of decay per 1,000 years. That's what the K is going to represent. But we do know that 3.3 thousand years ago, we were at 317. So since that t quantity goes back in time, then we'll use a negative number here. Now to solve for k, this is going to take a little bit of work. Hopefully you all can keep up with me because we've seen this before in a algebra class, but I'll kind of explain it and hopefully the pattern becomes recognized. If we're going after this k value, the first thing I'm going to do is divide both sides by 195.6. So, and I'm going to report this over here on the right side. 317.2 divided by 195.6. So that takes care of this term. Then if I apply a natural logarithm on both sides of the equation, that will eliminate the base of e. And so I'm applying that to both sides. And then finally, that would leave me with k times this quantity here. Then I could divide by this quantity and move it to the left side. Well, that's done after this logarithm was done, so I want to make sure that my division bar extends over the whole thing here. Divide by negative 3.3. And that work, those three steps, would allow me to have k by itself. So k is the result of the natural log of this fraction, all divided by negative 3.3. Now, it's not really necessary that we go to the calculator to compute this, but if you're curious, that's negative 0.1465. So that tells me that we're losing about 14.65% per 1,000 years, 14% of mass every 1,000 years. Now, the reason why I say it's not necessary that we compute this is because anytime that we reference k moving forward, we can actually just take this entire expression and punch it into the calculator. Now I'm running out of room, so I'm going to jump up here and finish out this math. We know our k value, we know our c value. Now we can answer the question, what would the mass be 5.9 thousand years from now? So y is going to represent our mass. We know as of today we had 195.6, and thanks to the knowledge of what was present several thousand years ago, and we know that this is e to the k times t power. The t power is 5.9, and rather than using the decimal for k, I am going to copy this whole fraction in here because I know my calculator can handle it. That'll be the natural log of 317.2 divided by 195.6, and all of that divided by negative 3.3. Again, that expression should generate the negative 14% times our 5.9 as a power over e multiplied by 195, and we get a result of 82.4097 milligrams. And that seems reasonable. There was 300 milligrams present 3,000 years ago. There's 195 present currently. So if we go forward another almost 600 years, then, or I'm sorry, almost 6,000 years, then we should be left with about 82 milligrams of that material. All right, so we'll finish out the video with this last question here. Another radioactive isotope question. This time we're talking about carbon. This isotope decays at a rate proportional to the amount present. So here we are again. So the amount present, we might call that Y, and we would call our time, let's see here, our time T, or we'll go to X this time just to show you that. So the dy dx rate being proportional to the amount that's present, there's our kx description. Half-life is 5.7 thousand years. Now here's something that's kind of interesting. We'll go through the process to ultimately show that y is equal to c times e to the kx power again. It's the exact same process that we saw before. But when we start describing this phrase half-life, that's an indicator that half of our initial value c is what's left after a certain amount of time. And in this case, we're told that that's 5.7. So even though we don't know the actual amount that we started with, we know that half of it remained after this portion of time. Now think about this. When we're solving for k, the rate of decay per 1,000 years, this tells us how much is left after 5.7 thousand years, half of it, but how much is going missing after 1,000 years, that's what the k value is going to describe. In the act of doing that, one of the first things we're going to have to do is divide both sides by c, and then immediately the c values cancel. So even though we don't know the initial value, we don't need to know the initial value, and we can continue to solve. Then we'll apply a logarithm to isolate the k times 5.7. Then we'll divide by 5.7. And ultimately we get to the description indicating that k is equal to the natural log of 1/2 divided by 5.7. And then if we consult the question again, how many years will it take for the mass to be reduced to 1/3 of its initial amount? Well, again, a little bit of a modifier to this problem. We'll just jump up here so we can see it all in one shot. If I wanted to get down to 1/3 of the initial mass, again, not knowing what the initial amount was for C, but this time we know that our K value is the natural log of 1/2 divided by 5.7. We don't know the time that it takes to get there, so now we're going to solve for T. And in much the same way, we could isolate it. So we'll divide both sides by C. That's a good starting point. Then we'll apply a natural logarithm to isolate e. So now if you're keeping track, we have the 1/3 that's isolated. We'll apply a natural log to both sides to get rid of the e. Then we'll divide all of that by this number. Now this number, even though it looks a little bit complicated, is just a number multiplying by t. So that's why we're able to divide it away. That's the natural log of 1/2 divided by 5.7. So we have this nested fraction here, which isn't the end of the world, but just be careful with your grouping symbols here. And then this expression ends up telling us what t should be. And the calculator is showing me 9.0343. And since we're solving for t and we use t representing time in thousands of years. So if you wanted to report this as 9,034.3 years, that's okay too. And that makes a little bit of sense. It took 5.7 thousand years to reduce to half. If we want to reduce all the way down to 1/3, so we have to keep going beyond a half, then 9,000 years being necessary, that doesn't sound unrealistic. So I hope that series of problems helps you out. You now have another column on the right side that you can work through yourself. I don't think it's a bad idea to practice both sides of the equations on your own. See if you can complete them without referencing my video or your notes. And if you can complete them both without any reference material, I think that's a pretty good sign for the start of our test next week. Thanks for watching.